A very good evening, everybody. Glad to see our quantum tech enthusiasts joining to know what it feels like to work with quantum, the smallest discrete unit in the universe, from our speaker of the session, Shashwat Kumar, a PhD student in electrical and computer engineering at Princeton University, researching applied physics and quantum engineering. Sigma Xi welcomes Shashwat and all our participants to Rendezvous Episode 3, The Research Stream. I'm Durgashri and I'll be your host for the session. Given the circumstances, let's try to make the best out of this virtual session at our hands today. The format of the episode is quite simple. First, we shall be talking with the speaker. Towards the end, we'll have an AMA round, creating a platform for our audience to interact with Shashwat. I would like to inform you that the students can drop their questions in the chat box and they'll be addressed at the end of the session. Without further ado, let's dive into the session to learn everything you're curious about quantum technology and the research life associated with it. Shashwat, how about you walk us through your professional life so far and acquaint our audience with your interests?
Yeah, hi Durgashri, and hello everyone here. Thank you for inviting me to this rendezvous episode of Sigma Xi VIT. Let me start with where I am right now. So, as you mentioned, I'm a PhD student at Princeton University. I'm in the Department of Electrical and Computer Engineering, and I research on quantum computing. So, my area of research is superconducting qubits. We are trying to make next generation qubits that are better than the current ones. So, this is what I'm doing right now. And I think I should start from where I had my bachelor's degree. So it was Aiza Mohali. So after class 12th, uh, I took admission in Aiza Mohali, and there I went because it is an institute for basic sciences. You can always study what you want instead of a particular or defined platform. It is not like that you go there and you have, say, physics as your major or chemistry as your major. In the first 2 years, you have everything. You study everything like physics, chemistry, maths, and biology. And then in third year, you get to choose your major. So that was the time when I chose physics. And throughout this time, in my first 2 years, I was exploring other subjects too. And at one point, I was interested in biology too. But I think physics was was my first priority always. And that's why I ended up choosing physics. And I started learning quantum since then. So after choosing physics, I did a couple of projects, research projects that helped me understand what quantum is and what is the scope in this area. Those couple of projects were at Aiza Mohali, including some reading projects, one project at TU Dortmund in Germany, and another project at EPFL in Switzerland. So after that, I started looking for PhD positions all over the world, and I was able to get into a couple of them. And Princeton is one of them, and here I am.
It's so interesting. Like, right after your 12th standard, you decided that your career will be in research. Not everybody will be able to make such a decision. Right.
Yeah. I think no. So that's an interesting story. I dropped a year after class 12. I was not sure what to do. Firstly, after my class 12, I took admission in an institute, triple IT, Indian Institute of Information Technology, to study computer science. I went there and I kind of didn't like it, so I decided to, to not go there. I mean, to not stay there and look for another college because I didn't like that. At that time, I didn't like that typical mindset that you're working hard to get a job. It was
It's
no offense to computer science, sorry, but yeah, I didn't like that.
it's an interesting decision actually because you get to pursue what you're interested in. You're not bound to work somewhere. Just a 9 to 5 job is not done.
Yeah,
And yeah, so given the truckloads of information and opportunities available out there and various resources available to research about all the domains of research, how did you identify that your interest lies in quantum technology? Like maybe there was some kind of project you worked on or some article you read. So, what is that interesting aspect of quantum technologies which drove you towards it?
or the movie you watched, right? So have you watched Ant-Man series? Like a couple of movies. Do you remember how much quantum they use? I don't think that's a scalable. Yeah. Okay, that was not the start actually, because the movies came after I started doing quantum. So it was, it was. I think it was due to one professor at Aiza Mohali who is very well known in India for quantum computing, for theoretical quantum information, and I wanted to talk to him in my first year or first semester at Aiza Mohali. I went to him and talked to him. Okay, I want to do quantum because I don't know, it was a buzzword. So uh, he gave me a project on special relativity. It was not quantum. I was disappointed. But I understand if someone from first year comes to me and says, okay, I want to learn quantum, I think I won't do the same. I would do something else. Maybe I'll refer them to, okay, go to Qiskit and start using Qiskit notebook. But yeah, he did this. And then I started reading it on my own. As you said, read some articles from various places, and I think Medium is a good platform to develop your interest into something that you want to pursue, or if something you are interested in, you can go to Medium and read some articles because experts try to write in very layman terms so that anyone can understand, and also some YouTube videos. I was kind of reading about Paul Dirac and Feynman at that time, and why quantum mechanics is so weird, and why did Einstein didn't like quantum mechanics. So all these things. I mean, Einstein by being a genius, why would he say, okay, God doesn't play the dice or something like that? That quantum mechanics is spooky. He made these statements, and he believed quantum mechanics is not complete and it is weird. So I
Yes.
think that was the point when I started to think that maybe I should go into it and see what's going on.
Okay, why did he call it so?
Yeah.
Okay, so quantum engineering has become a new trend in research, and millions of dollars are being invested to give life to the most optimal technology and to solve most unanswered questions. So, what are those thought provoking insights about quantum technology you think can interest any research enthusiast?
Yeah, I think you are right. You mentioned a couple of astronomical numbers in $1 million or whatever. You're right. So people are pouring this much amount of money, even in the universities, apart from big giants like uh, Google, Amazon, IBM, Microsoft. Uh, Governments are also funding their universities in their respective
Right.
countries to build quantum computer because it is supposed to have theoretically some applications that are a boon and also a threat to current cybersecurity system. So everyone wants to get an upper hand on this technology before any other person gets. So yes, you are right. So what are, as I mentioned, okay. So as you asked, what are some interesting aspects of quantum engineering? So I think I'll start with quantum computing or
Mhm.
quantum information because it's very easy to understand. So when you talk about quantum computing is a bit of supreme because of two quantum phenomena. The first
Okay.
one is the first one is called quantum parallelism. It's just like you have parallel computing,
Mhm.
and it's something like that. So it is quantum parallelism, And another thing is quantum interference. So if you have studied wave and optics in your class 12, if you remember, I think, what was that? You have water, and then you have two needles, and then you shake them, and waves are generated, and there is a constructive and destructive
Okay,
interference.
understand.
Yeah, similarly, in so since there is a wave particle duality, and I can say if there's a wave, there has to be a particle. I mean, this
Mhm.
is very hand wavy argument. Just don't believe that it is true right away. So quantum particles can also interfere because they have a wavelength attached with them, associated with them, and they are also particles. So since they can interfere, and there is something called quantum parallelism because of superposition, quantum
Mhm.
superposition, another word. So what is quantum superposition? In classical computing, say you have a 0 and 1 as the states of the bit. So either you have a 0 bit or 1 bit. In quantum, you can have a superposition of them. You can have both of these together, and until
Mhm.
you measure, you can't know which one was it.
Okay.
Or basically, both of them were there, but until you measure, sorry, when you measure, you see one of them. But
Uh-huh.
before this, both of them were there. So, giving you have superposition. Superposition gives rise to quantum parallelism, and after quantum parallelism, you have quantum interference, and all of this combined together make quantum algorithm uh, supreme, or a bit faster than, sorry, very faster than classical algorithms in some situations, in some particular problems. So maybe I'll give you an example.
Mhm.
Have you heard of, okay, sorry, I shouldn't say. So there's something called Grover's search algorithm. It
Uh-huh.
is uh, it is like, you suppose you have a very large data set and you want to search for something. Suppose you have something in mind. So just think of it like that, like this. You have a phone directory, and it is a
Mhm.
physical one. It's a book. And now you want to say search for Durga Shri. Okay, which one is Durga Shri? That's easy. You can go to D and do it, right? But
Mhm.
say your phone number is 1 2 3 4 5 6 7 8 9 10. Not this easy, but say your number is this. And now instead of going from name to number, you have to find the number and tell me which what is the name associated with that number. So this is a hard task. You'll have to
Yes.
look for all the numbers that are in the directory, starting from the first one. So suppose there are a million numbers in that directory, in that physical directory where you can't just search Control F and search it. And even if you do Control F, the algorithm is doing the same thing. It is matching each and every number in the directory with the number that you have entered. So
Exactly.
suppose there are a million numbers. What you will do is, what your computer or you will do is, you will take a million steps to check. And unluckily, if it is the last one, then you will have to finish all the million steps. But if it were a quantum computer to do it, there is something called Grover search algorithm. So Love
Mhm.
Grover, an Indian dude who I graduated from IIT Delhi, then he moved to the US to work in Bell Labs. Currently, it is Nokia Bell Labs. There he realized that you can use quantum mechanics or quantum computing, not quantum computing. You can use quantum phenomena in information science uh, to search something very small in a very big data. So it's like
Mhm.
a needle in haystack, something like that. So maybe I can tell you, like, if you have uh, 30 0 and 1, then they will be, say, 30 0 and 1. And if you want to make a sequence out of them, you will have maybe around a billion possibility of having a sequence. Of what sequence will it be. And your quantum computer can be in, sorry, your classical computer can be only in one of them at a time. But I talked about quantum superposition. A quantum computer can be in all those billions of possibilities at the same time.
Oh.
And you can, yeah, in principle it can be. And when you run your process, it is like doing a billion processes at the same time. So it is like a parallel classical computer. Only the only difference is in a parallel classical computer or parallel computing, you will use a billion different processors, but here you won't be. It will
Okay.
be your quantum uh, phenomena, or uh, yeah, it will be your quantum, I would say, supremacy that you will be exploiting in the single piece of hardware or the same hardware. You won't be requiring a billion copies of the same hardware. So
Uh-huh.
that is quantum.
Um,
So yeah, there's quantum parallelism.
okay, I just have a small doubt. So
Yeah,
does
sure.
that mean you're reducing the computing cost or you're actually increasing it? Because quantum computers will definitely be very costly.
Computing cost in what sense, like in terms of money or in terms of steps it takes?
In terms of resource usage, like in computer science, we have things, right? Like
Yeah,
for searching a few, for searching something in a list, you will
yeah,
have some cost.
yeah. So this is where I was about to come. So it reduces your cost in terms of resources,
Okay.
like time. So your time is a resource, right? So a classical computer would take like a billion steps to do it, and a quantum computer, which shows, sorry, not shows, with Grover's search algorithm, it can do it in 1,000 steps.
Mhm.
So it saves you time.
Okay, but what about money? Isn't it costly?
Yeah, it is. So yeah, it's a good question. So as you said, people are investing billions of dollars. Why? Because it is costly. You can't just bring a classical, bring a Mac at your place and start doing quantum computing. You can do it, but you will only simulate it. You won't be doing real quantum computing. So it's going to be very costly as of now, because if you want to do real quantum computing, firstly, we don't have resources. That is the hardware to make a billion
Mhm.
qubits. I mean, we can
Mhm.
make billion qubits, but not to control them at the same time. So we
Mhm.
don't have that hardware. And if even if you have that hardware, and the current technology is you have to cool down to sub millikelvin temperatures, not sub millikelvin, maybe sub Kelvin temperature. You have to go to uh, like 9 or 10 millikelvin to run a superconducting qubit at this time. So if you want to run all of them, you'll need a very huge fridge, like a dilution refrigerator. I'm not talking about the fridge that you have at home. A fridge that goes to like 10 millikelvins.
Mhm.
It's it's very close to zero.
So we are trying to balance time with money.
Yeah, I guess. But maybe in future we, I mean, there are so many audience here, and I'm also quite young. I think I'm almost of your age. So maybe we build a quantum computer that doesn't require to go to those extreme temperatures, and you can work at room temperature only, and you don't need a lot of money to do it
Future
because of the
improvements.
research of some people. Yeah.
Yes. Right. So people go into quantums just because it's interesting, it's a new trend, and there's so much more. Yeah, as you tell, it's fascinating me also. Like even I want to explore it. Apart
Mhm.
from interests, we tend to look for future prospects from the subjects we work on. Quantum tech shows great potential to lead the research world in the future. So, what
Mhm.
kind of opportunities can we look forward to in quantum engineering while it creates a sensation in this world?
Yeah, opportunities. So I assume you mean like opportunities for youngsters and
Yes.
the professionals, right?
Yes, as a professional, taking it up as their career.
Yeah. Okay. So right now, okay, I'm not sure how it happens in India, because in India you don't have many quantum startups or many companies doing quantum computing. But in the US, if you graduate with bachelor's in computer science or electrical engineering or even physics, you can apply to these places like IBM, Google, or Rigetti Computing, and you can interview with them, and they can give you some kind of job. Like they can give you a good job to sustain yourself and also do some research. So because quantum computing everywhere, or yeah, okay, quantum computing everywhere is still in its native stage. We have not reached the point where we have fully functional quantum computers where we just want to manufacture more instead of doing R&D. So still we are in the R&D phase. So the job hirings will be in the R&D, not in sales and
Okay.
manufacturing. So at this point, you can think of going into, say, quantum computing as a research scientist in some company. And there are other aspects of quantum technology too. So you said quantum technology, yeah. I like this because quantum technology is not only about quantum computing. There are so many things to it.
Mhm.
Other thing that people are interested in and people are exploring is called quantum sensing.
Okay.
So quantum sensing uses quantum phenomena just like quantum computing,
Mhm.
and it can sense, since sense is there, so it can sense very small magnetic fields, say, that are crucial to many things like weather, maybe earthquake, to cure some diseases, for diagnosis, and for also communication. That is
Mhm.
also called quantum communication. So quantum communication, I believe, comes from. Is possible because of quantum sensing, because you can sense the signal. I mean, you can send a signal and you can sense the signal from at the other side. So quantum sensing has so many applications. As I said, the first one is magnetic field sensing, and magnetic field sensing is vast. I mean, it is like it has applications starting from an electric car to sensing your brain waves. So um, I've worked on one quantum sensing project in my master
Uh-huh.
for my master's thesis,
Okay.
and I remember, I won't name the company, but one of big car giants in Europe, they
Mhm.
approached us uh, for our sensor and asked us if they can, if it is viable to use it in their car.
Mhm.
So quantum sensing is also there, and also communication, like make quantum internet or quantum key distribution. That comes to cybersecurity. Yes, so it has vast applications, and quantum sensing is the field which is quite developed. It is not like quantum
Mhm.
computing. So there are companies that are hiring people in quantum sensing for manufacturing and sales purposes too. So you can just go there and contribute yourself. It will be like another job.
Okay. So just apart from processing, we are also including this into automobiles. So.
You can. I mean, yes, there's a possibility if we work hard. If you would have taken that project seriously, maybe it would be a reality by now. But yeah, I think people are looking into it. So if one person can think it, another people could also think it. So this is the
Right.
thing, right?
Okay. So, yeah, there's something I wanted to ask you. We came across
Yeah,
Cutie Pie. The name is quite
yeah.
cute, actually.
Thank
The
you.
initiative you have taken to make quantum technologies accessible to everyone in terms of knowledge and opportunities. How did you
Mhm.
hunt for like minded people and devise a plan to develop such a community? Like, what was the trigger for that?
I think, yeah, I should tell you a story for that. So this Cutie Pie thing started after I graduated, and it's not only me. We have a team, and Cutie Pie started because some of us who are interested in uh, quantum in some sense, we all graduated, so we were all from the same batch in Aiza Mohali. We graduated and we didn't have much to do, so we just started talking about each other's research. So what we did in our master's project. And so that's how Cutie Pie started. So it was not called Cutie Pie then. It was like, I think it was called uh, Aizel Mohali Quantum Chapter, maybe. It was very unofficial. And then we thought that maybe if we like our talk so much, other people would also like it. So we opened this to other people too, to Aizel Mohali community.
Mhm.
And we got a very good response in the beginning that yes, people are interested in knowing what they want to know or what we did in our master's thesis or our research. And then so one of my friends, he came up with the name Cutie Pie. So it is, of course, uh, it is it is motivated by PewDiePie, but yeah, I mean, he came up with this name. Okay, so let's name it Cutie Pie, and we are like, okay, sounds good. And then we opened it to other institutes like IIT Roper. IIT Roper was it is very adjacent to ISO Mohali, and then we started reaching out to our contacts all over India and abroad. And then we made this community. We had this Discord server, and like 300 or 400 people are registered with it right now. So how we make this community? I think we just talk, we just outreach, we just say, okay, I want to do this, I want to do quantum computing, and if you are interested, let me know. I mean, we can do something together. Or I want to read about this paper that just came out recently, and this paper talks about this interesting thing. Do you want to know about it? Okay, let's read it together and discuss it. So making a reading club is a good habit or a good thing where you can attract like-minded people, and also like kind of advertise it a bit, like let other people know, yes, you are interested in doing something, so that they can also join.
It's important to share because there are so many people who don't know stuff, but they are looking for it. And this is really an appreciable initiative.
Yeah, thank you.
So, would you like to tell us about the kind of projects you work on with the Cutie Pie team?
Yes. So, what we do in Cutie Pie is we the main thing that we do right now is we outreach to different people, and we ask them to give a talk for us in their field of expertise. So when we started, so it was mostly us, like people who were in Isomohali or who started that small group of Isomohali quantum chapter, something like that. And then we started reaching out to other people, as I said. Then we had people from IIT Roper and other people from Isomohali who were interested in giving a talk or talking about their research.
Okay.
And we had someone from, I mean, we had people from maybe IIT Bombay, Kanpur. I mean, we reached out to people whom we knew only. I mean, it was not like we just randomly emailed anyone. And I think we could do it. I think the next step would be to just advertise it more. But before that, like, as I said, what we work on. So we ask people, are you interested in talking about your research? And we ask students usually. So students don't have a stage to, present their research work usually. So we just ask students. So you did this thing in your master, or you think you did this in your bachelor's, some internship. Do you want to talk about this? And we keep it very informal. Like at any time, anyone can interrupt and ask, okay, what happened here, or I don't understand. So it's very informal discussion. Initially, the session used to be for like 1.5 hours to 2 hours. It was really long and exhausting. But now we try to keep it to 1 hour. But the idea is we ask our speaker to convey the main idea, because the target audience is always first year, second year, third year students. Um, to convey the main idea so that people can build their interest, or if they are interested, they can read about it, and they can also contact the uh, speaker. So uh, so last month, I think this month only, in January, we had someone from IIT Madras, another student, talking about his research. He talked about quantum. He talked about Schrodinger's cat states. The name is very fascinating. And next month, that is next week actually, on this day, like on Saturday next week, that is Feb, we'll be having another session, and I'm very excited for it. It is by someone at IBM, and he is working on uh, quantum machine learning. I have some idea about machine learning. I have some idea about quantum, and I'm not sure how do they go together. And so he's a research scientist, and so as you also asked what opportunities you have, so what he's working right now as a research scientist is the opportunity that one can have after graduating with a degree in quantum physics or after doing a PhD in quantum computing. So we'll be having that session, and then we are targeting other people from academia and industry. And other students also. So student slots are always open where they can come and share their ideas, what they talked about. And the good thing that came out of it was people are, I mean, interested students reach out to us. They say, yes, I saw this thing, or you organized this thing, I saw this and I'm interested. What should I read? So they either connect to the speaker or they talk to us, and then in the regime of our knowledge, we tell them what to do. So this is what we do at Cutie Pie.
Uh, so we definitely need a team to collaborate, talk, interact with like-minded people. I think this Cutify is actually doing it so well.
Mhm.
And
Yeah,
okay, yeah,
yeah. I mean, team is always important because you can't do it alone. You have other things to do also, right? You are
definitely.
like you have assignments to do in your stage. In my stage, I have research to do. I have to go to lab and maybe cool down my fridge. Okay, that's what I did yesterday. So it's the same fridge that goes to 10 millikelvin or something. And so you have so many things to do, but at the same time, you need to keep connected to people who you think they are. I mean, they think like you. They have similar goals. They also want to make the world a better place in terms of quantum. And yeah, so you just keep connected to that team, and then it keeps happening.
Sometimes you're just discussing and randomly an idea strikes and that becomes your project. Just imagine how interesting it could become. And this is possible only when you have like-minded people around.
Exactly. I think you're right. I think you're right. Of course. I think
So,
that's what happened with Cutie Pie.
oh, interesting.
Yeah.
Okay, now let's talk about your journey into Princeton. So
Uh-huh.
it was, I believe that it's not a cakewalk to get into Princeton University. So how was the process right from filling out your application form to getting admitted as a PhD student? What kind of projects did you work on in ISER Mohali as a preparation for the same?
Yeah. So you're right. It's not a kid's walk, and it took me like 5 years to prepare for it. If I should be honest, like starting from the first year, because everything counts from your grades, from your project, from your skills to talk to people. Everything counts when you interview for the grad school. So yes, it was. So I started application process in 2020 November. I was a bit late because the reason is I thought I won't go to the US because yeah, because of capitalism and all. I know, I'm just kidding. I thought I won't go to the US because I was happy at EPFL where I was having my master's project. But then I talked to a couple of students and my seniors and someone in my lab who is still a very good friend of mine. He was my supervisor at that time, and he suggested to me, okay, apply to as many places as you can. Don't leave a single place, unapplied. Always apply to. It will cost you money, of course, but you have to apply. So I started applying to so many places in Europe. I started Europe. I thought, okay, I'll stay in Europe, or maybe I'll go to Asia because that's close to home. Europe is also kind of close to home, but US is like even now it is 10.5 hours time difference. You have evening, I have morning. So I thought I won't apply. But then another friend of mine who is senior in the same lab I was working in, he pushed me to apply to the US. And I thought about it. I took TOEFL and I applied. I didn't take GRE because GRE was not required this year or that year for me.
Okay.
Yeah. So, and also I didn't have time. I mean, if it were for GRE, if I had to prepare for it, it would have taken a long time. And because I thought about it in November. And then I applied to a couple of universities in the US and also in Europe and in Asia. And in February, I started to hear back from them. There were a few rejections. Of course, there are always rejections. There were a
Yes.
few acceptances. And one of the acceptances was Princeton. And then I went for Princeton's visit day. It's kind of an open day for all people who are interested. I mean, who have admitted who have been admitted to Princeton and they want to see what's in Princeton. So
Okay.
there was this virtual visit day. Due to COVID, there was no in-person visit day. So I talked to my potential PIs. PI means principal investigator or my supervisor. I
Mhm.
talked to a couple of people, and now I have joined one of them. So this is good. So this is how I think I came to Princeton in terms of application process. But when you apply to, I mean, when you apply to any grad school, there are so many things that are considered. I think your grades are important first of all because they want to see like you are what you can do your work. So if you're assigned to do something, you can do it. So grades
You're
is a good
dedicated.
thing. Yeah. I mean, there are things where grades don't matter. I mean, if you want to do a business, maybe grades don't matter. If you wanna, I mean, if there's some task that doesn't require you to have good grades, you don't pursue grades. But if you think you want to go in academia, academia is very grade biased. So usually either you have like a very good profile, like you have published tons of papers and all of those papers are really good, or you have good grades, or both. So there are people in all the spectrum. So I was the second guy, like okayish grades, not very good also, okayish grades. I would say okay, decent grades, um, some research experience,
Mhm.
and I applied to as many places as possible. And I think good letter of recommendation. So that is important. So since I worked with many faculty uh, at many faculty members in Eisel Mohali itself, and then I worked with the professor in TU Dortmund and with two people at EPFL in Switzerland.
Mhm.
So all of them gave me, I believe they gave me very good record. That's why I'm here. So I got recommendation from them. And
Mhm.
another important part is your statement of purpose. So statement of purpose has to be like you should start writing it as soon as possible. Don't wait till November like me because it takes a lot of time. Every time you see it, you will find something to play with or play around. You'll say, okay, not this word or not this sentence, or this is not important. So because you have to tell your life story in your own
Mhm.
words, you don't have to say, okay, since my childhood I was interested in this. It doesn't work. It works nowhere. You have to tell them why you are interested in it. So I mean, I think
What
I also
experiments did you do?
what experiments did you do or where you failed. So there are a few universities which specifically asked us, okay, tell us your failures also and write a paragraph about it. So I think everything is very important, and I think uh, the point of reminding you of your failures is to check your personality. How do you treat them? I mean, whether you learn from them or you want to hide them because no one in this world is like, no, I
Perfect.
never had a failure. So I think SOP is a mixture of everything. So
Mhm.
these are the important elements. First one is your letter of recommendation. Second, your
Mhm.
statement of purpose, and then your grades and your research experience. If you combine all of them, I mean that what makes a good profile.
So those few lines can decide your future, where you'll study, where
In
you'll
that
pursue your PhD and everything. I mean, the statement of purpose,
the statement of purpose and especially in academia, the letter of recommendation.
recommendation. Yeah, as you're mentioning about the letter of recommendation, how are we supposed to approach our professors for the same? And how helpful is it going to be to choose the right professor to mentor you in your PhD?
Yes. So uh, how to approach your prof for letter of recommendation? Okay. It's like so when you start working with someone, it's like building a relationship. You slowly start to talk. You talk to them about their interest in research, your interest in research, and then you have some agreements and disagreements, and based on your interaction with your supervisor or your professor, and the based on the and the kind of relationship you have built with your professor, this is what gives you a good letter of recommendation. I
Okay.
mean, you can take someone's course, like I can take X professor's course and I can get A plus and A plus, like the best grade possible. But if that person doesn't know me or if I haven't interacted with him or her anytime in past, I think he can't write you a good letter of recommendation. He would only say, okay, this person was in my class. He
Mhm.
seems brilliant because he got an A plus in my class, and that's all. He doesn't know about your personality. So whenever you are applying to any academic position, be it masters or uh, PhD, um, the university that wants to, that will be admitting you, they want to see what kind of person you are. And this comes from the words from your professor or people whom you have worked with, because they are experienced, so their words are given more significance than your own words. If you say, okay, I am this, okay, that's your SOP, right?
And this
But
also talks
what
about your interest to learn.
exactly? I mean, exactly. So if you keep bugging your professor, hey, how is it happening? How is it happening? Then maybe they can write, yeah, this person is curious. So yes, so as you said, how to approach your professor. So I think the first thing to do when you want to ask someone for a letter of recommendation is to talk to them. Talk to them about your interest, what you want to do, what your aim is, whether you want to be in academia or you want to go to industry, whether you want to do research or you are aiming for a job. I think it's the same thing what I said before. But the thing is, you want to tell them. And the same thing, based on the professor's experience, they are going to write it in the letter of recommendation.
Great. It's
And
not a 1 week process. It
it's,
definitely
it's
isn't.
no, not at all. I mean, if you want a good letter of recommendation or an honest letter of recommendation that resembles with your SOP, because you have written something in your SOP, right? Based on your experiences. And you have also talked to your professor, right? And if these two things don't match, because you can't see what your professor is writing, if there's a big mismatch between the two, I'm pretty sure no one will take you. So
Definitely.
always,
Even yes,
yeah,
yes.
always tell your professor what you want to do, and how to ask them. You want a letter of recommendation from them. It's very straightforward. Write them an email, and a humble email saying, "Hey, professor, hope you're well. I took your class, or I did this research with you. Hope you remember me. I'm applying for this university. I want to do this. Say, I want to be a quantum mechanic, and I think this university is going to be a very good opportunity for me. If you could write a letter of recommendation based on our interaction or based on your experience with me." So this is how you approach. Very straightforward email. Uh, just go for it. And if the professor is interested, he or she will give you. Sometimes professors are busy because they have a busier life than yours. You don't have so many things to do. They have so many things to do, like writing grants and also being in administration, teaching classes, and doing their own research. So this is a lot of stuff to do for a single person. So they may ignore your email, but don't be discouraged by it. Humbly send them another reminder. I mean, just follow up on that within a week or so. So this is how you do it. I forgot what was
Great.
the second part of your question.
Yeah, how's that going to help you in finding the right professor to your
Yes.
PhD? Because
Oh,
you need a
yes.
right mentor.
I think yes, exactly. It's a very important question because when you go for a PhD, again, when you go for a PhD, you are working with a supervisor, and I think one of the professors at Princeton uh, gave this analogy, and I will quote her. So she told us. Uh, Choosing a professor is not like buying a car that you go, okay, so I don't want this, I don't want this feature, or I don't like this steering, or maybe I want something more, or maybe engine should be better. It's not like buying a car, okay, what you want. It's more like a marriage because you have to stay together for next 5 years. You
True.
have to get to know the person. I mean, if you're a professor and you have a personality mismatch, and that becomes toxic, your next 5 years are ruined. And there have been cases where people have either quit their PhDs or after finishing their PhDs, they have always cursed their professor for the rest of their lives. So to choose the right professor, you need to talk to him or her. You need to talk to them. Talk to as many people as possible, and always remember to ask this question: what kind of supervisor are you? I mean, what do you expect? So you ask, right, when you go into a relationship, any kind of other relationship than a academic relationship, you ask this question: what do you want out of this relationship? The same question you ask your supervisor. Okay, what kind of supervisor are you, and what do you expect out of this student mentor relationship? Do you want me to work very hard? Do you want me to work on this project? What do you expect? Do you have hard deadlines? Do you mind if I miss a couple of deadlines? Okay, how hard are you about coming to the lab? Do you mind if I come at 12 instead of 10? Do you mind if I stay late? So all these things you have to ask, you have to check with your supervisor, and you can't do it in 1 hour because so say you are accepted at some position X, and then you're talking to the professor, and he says, okay, we can talk for 1 hour. So in that 1 hour you want to ask as much as possible because that person is busy, and that person will hardly be giving you time again. So ask these questions. These may sound embarrassing at first, like what kind of supervisor are you? Or it's like asking, okay, yeah,
But
what
if
kind of
it will
mother are
cost you
you?
5 years, it's
Yeah,
definitely.
I mean, exactly. So to choose a right supervisor, you need to talk to as many people as you can and ask them right questions and then find the right match for you. And a good thing about Princeton, I want to thank Princeton for this. Princeton didn't admit us into any lab. They admitted us in the grad school, and
Uh-huh.
this grad and and in grad school, I mean, it's not like Europe. So I think I should make this distinction. In Europe, usually, when you are admitted for a PhD, you directly go to a lab,
Okay.
and you hardly have, until you have interacted with that person before, you hardly have an opportunity to ask that person questions about himself or herself and get to know him or her. But in the US, in most of the universities in the US, you go to a grad school and then you have rotations. I mean, you have liberty to work with anyone. So you are
Okay.
admitted to a department and you have a liberty to work with anyone you want. And this gives you enough exposure to get to understand what kind of personality that professor has and is it a right suit for you. So this is what happened to me, and I think I recently found my advisor. By the way, since you mentioned this question, last week I got. I mean, I finally decided, or I knew who my advisor will be, and like a couple of weeks ago, on 10th January, I mean, all of us submitted our advisor preference form,
Uh-huh.
and
Okay.
we could fill that form only based on our interaction
Right.
with the professors. So I mean, this is something that happened to me very recently, and I'm excited about it, and I'm also excited about talking about it because uh, I've been through the process. So it's very important to find the right person for you.
Experience speaks.
Yeah, it does.
I mean, sometimes uh, people might expect you to stay on deadlines. They might expect you to submit it on time. But you think maybe if they had given me 2 more days, I could have done it a lot better. So
Mhm.
sometimes having flexible deadlines is also a boon.
Yes, it is.
And it is the same with the community, right? Say, for example, you're working with friends or
Mhm.
like-minded people. You're working on a project. If
Mhm.
everybody else is only worried about finishing the project, then there's no good outcome. But if your target is your outcome, then you cannot work on deadlines at times. So you just need a very good like-minded community of people. And
Yes.
it really sounds interesting to work with a group of individuals passionate about the same thing as you are, in new discoveries and new ideas
Yeah.
floating around everywhere. So how do you
Yeah.
think you can build such a community where people are so interactive and you can collaborate to work with them on research projects?
Yeah, it's more like an assembly. I mean, we can build a community, but I think build is, yeah, I mean, it's not one person who does it. When everyone agrees, then this community takes place, or this community comes in existence. So, as you said, you need to, outreach to people. So, if I assume like there are so many people here, and if they want to listen to something that is about quantum, then this person is interested. You talk to them, and oh yeah, if I mention quantum computer, what do you think? Like, is it possible? And someone says, yeah, it is possible. It's very exciting. That's good for you. I mean, this person is interested. Or someone says, no, this is not the reality. This is very far fetched. This won't happen. still that person is interested because that person got to know about it, that this is very far-fetched and this can't happen. So there was a thought process, and you can go dive into it, right? So you always talk to people, and uh, you ask them, will they be interested? Will they be interested in any such initiative that you want to take? So
Right.
I think, uh, based on my experience, I think it's okay. Forget it. I think it's like you have assignments, right, in the classes, and sometimes assignments are hard, or sometimes you don't want to put so much time into it because you have other commitments too. You want to have fun. You are still in your bachelor's. What do? You collaborate with people because all of them are starving for the same thing. They have to finish this assignment, right? So I don't know if your university allows it or not, but usually universities allow it. Until you copy it, you can discuss the assignments. So it's just like that. You discuss your assignments with your friends because all of them are motivated by the same stimuli. So I think that's how it works. So if someone thinks that I have to do assignment and like 5 or 10 of you come together and do it together, same way if you want to do you want to build a community of research enthusiasts, you just ask them, I mean, do you see yourself as a researcher? Do you think research is fun? Do you think teaching is fun? Do you think learning new things is fun? And if they say so, you just maybe you can take the first step and you can organize something that is interesting and that you think is interesting for everyone, and you invite them and you see what's the response. If it works out, good for you. You have something. If it doesn't work out, no problem. Either change your strategy or find new people.
Right.
So I think that's how it works.
That's good. Okay, now let's have a discussion about your projects. You worked on a few projects in ISO Mohali and you were a summer research intern at your Dortmund University. Can you brief us about those projects you worked on and what kind of experiences can we expect to gain doing internships?
Yeah. So these internships that I did are very different from any industry internships. These were research internships, and research internship would mean, I mean, my experience of research internship was to learn something new that was out of my um, current coursework. So the first so as I said, I stayed in ISO Mohali for 5 years. So after the completion of first year, and during first year, I started. I mean, I contacted a professor that I was interested in. He's a big name in India for quantum computing, and he gave me a project on special relativity. And I studied special relativity because it's very interesting. I mean, it's. I think it was the first time. It is weird. It is not, I shouldn't say as weird as quantum mechanics, but it is quite weird. It's very counterintuitive that when you move, um, when you start moving, the world around you shrinks. This is very counterintuitive. Yeah.
Okay.
Yeah, so
Sounds
this
like a
is,
fantasy.
yes, it is. But I mean, you can only observe it when you are at near the speed of light. So yeah, that's special relativity. And then at the end of first year, I studied again. I continued my special relativity project. So I was just reading it. So this internship slash project just was about reading about special relativity, light, some interferometer, and like in late 1800s there were a few experiments that demonstrated. I mean that set the stage for special relativity, why it is important. And in my second year, so in my first year I studied this. In my second year, I was interested more in optics or quantum optics. So I studied and I worked with Michelson interferometer. And so it's like interferometer. I won't say what it is like, but it uses interference, the same interference that we talked about initially, where you have constructive and destructive interference. And also studied some quantum interference, quantum interferometer, and that's when I started being serious about quantum. I started watching MIT OpenCourseware, where I found a couple of courses that were really interesting. I started following edX.
They are really interesting.
Yeah, edX is great. edX and MITx are great. Yeah. And after that, I started looking for opportunities near me that for an internship or for a project in quantum computing. And at that time, I didn't know that. Okay, so I started looking for opportunities outside IISER Mohali, and I didn't know something that there is a very good opportunity in IISER Mohali itself, and that I got to know only in my fifth year. But
Okay.
that's okay. Like this is how it happens. Uh, but the thing is, uh, after my second year, I was very much interested in quantum, and I applied for. Yeah, I also wanted to go abroad. I mean, everyone wants. So there's this opportunity that is called DAAD. It's German Academic Exchange Services. Its abbreviation is DAAD. They provide a scholarship to go to Germany and do research. And I applied to a lab for quantum information processing, experimental quantum information processing, and I got into it. So that was my uh, third year research internship. And maybe I can give you a brief overview if I can share my screen. Should I?
Definitely,
What I did?
definitely. Yes.
Okay. Uh,
So was that a remote internship or
no.
you?
That one was in person. I went there. I lived in Dortmund for 3 months, and
Oh,
yeah, and I visited Europe. I went to so many cities outside Germany. The scholarship was
okay.
only for Germany, but you know, money was there was a lot of money. I could go to France, Brussels, Amsterdam, Switzerland, Czech Republic, just to name them. Yeah. So apart from that, I mean, the only point of saying this is with internships uh, you get places to go to. Yeah. So okay, so I want to talk about my research internship at U Dortmund.
Okay.
So this slide in front of you, this quotes something from Richard Feynman, which he said in 81 in Caltech. I may be wrong, but I think it was in Caltech during a lecture. So the discussion was going on, and then he said, "Okay, if you want to, can you simulate quantum phenomena on a classical computer?" The answer was it's very hard, or no, because quantum particles have so many free parameters, while classical computers uh, will run out of memory, or they don't have uh, computing power to do it. And it was in 1980s. Like at that time, we didn't have an i9 processor or GBs of RAM. It was not. Yeah, it's not that time. So Richard Feynman comes up with the idea. Okay, why don't you make it quantum? Just use quantum entities for computing, not classical entities. If you want to simulate, if you want to see how physics works. So this was the founding stone of quantum computing, or the idea of quantum computing. Uh, why quantum computing is necessary, or who started it? I think Feynman's words, these words of Feynman, is what laid the founding stone for quantum computing.
Quantum computing.
So next, okay, I think I should give a brief overview. I talked about quantum parallelism and superposition, so I think I can talk about superposition a bit. So in classical computing, you have 0 and 1, right? You can either have 0 or you can have 1,
Yes, yes, yes.
right? But then Richard Feynman comes in and says, just make it quantum, right? Because it is not good enough for it's not good enough for the kind of physics I do. Just make it quantum. And in quantum mechanics, as I said, you can have a superposition of 0 and 1. In classical bit, you had either 0 or 1, but in quantum, you can have a superposition of 0 and 1.
0 and 1. Okay.
So this state here on right, that is 0 plus 1 whole divided by square root 2, this is called uh, a superposition state.
Okay.
So my system will be in this state, and when I measure it, there's half probability that it will go to either 0 or 1. And that half comes from the square of this root 2, 1 over root 2.
Okay.
So Richard Feynman's motivation, and people started working on it, and there's superposition. Okay, then we can use this state. So now think. So this is only one bit or one qubit, just like a classical bit, where you have a superposition of 0 and 1. Now assume you have like so many qubits, so all of them will be in superposition like this, and they can be in superposition with each other. So that's what gives rise to quantum parallelism.
Okay.
And then you can extract your results out of it using quantum interference. Yeah. So in my third year at TU Dortmund, this is what I did. I did quantum information processing, experimental, because theory is very, very well established. It is, I mean, theory says this can happen, that can happen, so many things can happen. But in experiments, I think we are not still there. So I was very curious, okay, what's not working or what's happening? And in my first summer internship, I found the culprit. But anyway, I'll tell you what I did. So I worked with something called diamond envy centers. Diamond envy centers, as the name suggests, it's in diamond. I mean, the diamond that people like to wear or like to boast about. And if you have nitrogen impurity in it, your diamond start to, I mean, any pink diamond you see, it has nitrogen impurity in it. So if there's nitrogen impurity and there's a vacancy next to it, that is a carbon atom just pops out, then you have some weird, and also, yeah, then it captures one electron also. Instead of vacancy, you have, I mean, at the place of vacancy, you have an electron. Then it has some electronic structure that can be exploited as a qubit. So I studied that. So on your left hand side, you see what the diamond envy center structure is, what it looks like. And on right hand side, what I'm trying to show is that you have nitrogen, right? I said there is nitrogen inside it. So nitrogen has electron, and that electron, nitrogen is there, and there is an electron at the vacancy location, and that electron has a spin, and that electron can interact with this nitrogen or nearby carbons. That could be 13 carbon or 12 carbon, normal 12 carbon, and we can exploit these interactions and make them work as a qubit. So this is what I did. I did quantum control of these things. I prepared qubit states, 0 state and 1 state, on a real quantum system, not in simulation. So this was a 3-month project. 3 months are quite short in experimental research. So that's the only thing I could do, was to to prepare my system in a state. And so this was the time when I was in TU Dortmund. It was in 2019. At the same time, thanks to DART's funding and Schengen visa, I had an opportunity to visit Switzerland, where there was a conference going on that was on diamond photonics. And there I met my future supervisor. He was the host of that conference. It was in EPFL. And I talked to him and I told him, okay, so I'm working on this, and what you are working on. So he was working on quantum sensing. Quantum sensing is about sensing magnetic fields using quantum phenomena. And I talked to him. I told him, hey, I want to work with you. Your research sounds cool. He said, okay, if you want to work with me, send me an email in September or October. And I did that. We had a few exchanges, and then we agreed upon something like funding, where will I stay, how long it will be, so many things. And then I went to Switzerland, went back to EPFL, and worked on quantum sensing. So that's my master's project. I think I can talk about it now.
Yes.
So what is quantum sensing? I will give general overview.
Okay.
So let's go back a bit. I told you that there is, so again, everything right now is on diamond envy center. So you have this diamond envy center, and it has this electronic spin E. Oh, by the way, can you see my cursor?
Yeah, I think I can. Can you just move it?
Yeah, I mean, does it seem moving?
No.
Okay, okay, leave it. Don't worry about it.
Okay.
Yeah, no problem. So on your right, you see an electron, and it kind of points upward, right? It sees. I mean, there's an arrow and there's a cone on the top of it. It looks like an arrow
Uh-huh.
pointing up the electron.
Mm-hmm.
So this is called a spin, the spin of an electron. So when this, if this individual, if this spin is just the single thing in vacuum,
Mm-hmm.
and you apply a magnetic field in some direction that is not
Okay.
parallel to the direction of spin,
Mm-hmm.
you will see that your spin starts to precess. It starts to
Mm-hmm.
rotate around this magnetic field with a frequency that is proportional to the magnetic field.
Okay.
Yes. So now, if I apply a bit, I mean, if I apply more magnetic field, say if I applied instead of B naught, I applied B1, whose magnitude is greater than B naught, it will
Mm-hmm.
change the omega naught, that is its frequency of precision. And you can measure this omega naught because you can make some optical measurements and you can know what is the frequency of this precision.
Mm-hmm.
And with that, you can know how much magnetic field did you apply. So this acts as a magnetic field sensor, a quantum magnetic
Okay.
field sensor,
Mm-hmm.
diamond sensor. So now, if you have so many of these spins, like many spins, they interact with each other. That's a different story. But now, if you have so many spins and you apply a magnetic field,
Mm-hmm.
then what happens is you can exploit this phenomena even better because there are so many spins now. And you have not only one spin but so many spins sensing the same magnetic field, and
Mm-hmm.
uh, you should have better sensing to magnetic field, and especially if they are interacting with each other in a constructive way.
Okay.
So what my project was, I combined these two. What it was,
Mm-hmm.
magnetic field, so many spins, and these spins are interacting with each other in a in a quantum fashion. They are interacting with each other in a quantum fashion.
Mm-hmm.
Then you then I firstly proposed along. I mean, of course, I worked with my supervisor, and we saw that yes, you can improve magnetic field sensing with this technique by three orders of magnitude. Like
Mm-hmm.
if you could initially sense 1 Tesla, now you can go to 1 millitesla. And these are not the exact numbers. Exact numbers are like 10 to the power minus 15 or 10 to the power minus 18.
Mm-hmm.
But just to give you an idea what it
Idea.
means. So
Mm-hmm.
now you can sense even weaker magnetic fields. And we were doing experiments on it. And
Mm-hmm.
I think experiment on this would require a long time.
Mm-hmm.
I mean, maybe a couple of years. So this experiment is still going on in EPFL
Mm-hmm.
where I worked. And my part in this project was to propose this. And for the rest of my thesis, or most of my thesis, I worked on the experiment design and to make things work for this. Yeah. So
Early
this is what I
seemed
did in my
just,
master's
yeah.
project. Yeah.
Okay. No, early seemed just like something intuitive, but if you're able to work on it, experiment on it, I think it
Yeah.
was definitely an interesting process during your master's thesis.
Yes, I think yeah, you are right. I think that was the second time I had some hands-on experience with all the setup
Mm-hmm.
that with which you can control quantum systems, for example, diamond entry centers, or how to operate a laser, or even how to handle tools, how to install a mirror or a lens or a
Mm-hmm.
beam splitter. So all these things, yeah. So it was very optical project, and I really enjoyed it.
Wow.
Yeah, I think that's all. So maybe I can stop presenting.
Um, no, you, okay. Yeah, sure.
Oh, sorry.
No, it's okay. It's okay. So we have a question from our audience.
Yeah.
Akshit Chowdhury is asking. So basically, qubit is core extrapolation of many walls theorem.
Oh, wait, what? Many walls?
Many worlds theorem.
Ah, many words because of superposition. See, Akshat, Akshat is his
Yes,
name.
he's Akshit.
Akshat. So I'm sorry. See, I'm not a string theorist, and I don't know if there is a multiverse or if many words exist or not. But still, I think people. So it's a postulate. Um, that's okay. So it's this is how we start. We start with in quantum mechanics. We say we can have a superposition of 0 and 1, like 0 plus 1 by root 2, as I showed. Is the superposition, and it's the property of this world where we live in.
Mhm.
And nobody, I think at least in the textbooks I read, nobody ever mentioned that it is because of interference with other world.
Mhm.
So maybe it is, like, maybe you research it and you find out, yes, there are parallel universe, or there are uh, other things that are not still understood, or why it happens. I'm not sure,
Mhm.
but this is the property of this universe, or this world that we live in, that 0 and 1 can stay together when they are in the quantum regime.
Great. I think that answers your question.
I hope,
Um,
yeah. I mean, I am sorry to disappoint you that I didn't say yes, yes, you are right. Superposition is because there are so many words. No, I don't think so. But maybe it is. I mean, that's the beauty of science. You never say no, you never say yes.
there's no end to exploration.
Exactly.
Okay. So, can you give us a few insights into the real life applications of quantum engineering?
Okay. Yes. So I think, yeah, real life applications of quantum engineering. We have been talking about it uh, till now. Like, we can have quantum computers where you can compute with better. I mean, you have some kind of supremacy in computation, and
Mhm.
you can have quantum sensing where you can sense better magnetic fields, or you can have what you can simulate physical systems. So there are so many things. So I think, yeah, you are right. I shouldn't have taken down my slides. I have to put them back on. Yeah. Just a minute. Okay, I have to go all the way up. Okay. Yeah. So as I see it, I mean, you asked the
Mhm.
real life applications. So as I see it, quantum technologies can be broadly divided into two parts. The first one is quantum computing. That is, like, that's the buzzword. Everyone talks about it. Everyone is so excited about it. People are
Mhm.
putting so much money into it. And other very important and crucial aspect of quantum technologies is quantum sensing.
Mhm.
And without quantum sensing, you can't have quantum computing. So quantum sensing is even basic. I mean, if you even if you have quantum computing, you won't have quantum communication. So
Okay.
quantum sensing is like the empowering tool that gives you ability to
Mhm.
do good things with a quantum computer. And
Great.
yes, so communication is important, and
Mhm.
quantum sensing enables quantum communication. So
Mhm.
on your left, you see a picture of a chandelier. So this is not a chandelier. This is a fridge. This is the same fridge we work with, and it goes till 10 millikelvin or even low. I think this looks even fancier. It should go even lower.
Mhm.
And on right, you're seeing some layer of maybe some material, and up and on the top, in the green part, you have a single spin in a cantilever that is
Mhm.
sensing the magnetic or electric environment of that material. So just to give you a picture of what it is, on right side you see quantum sensing, on left side you see quantum computing. So what you can do with quantum computing, and I will only talk about what I know.
Mhm.
So I work on superconducting qubits. So with superconducting circuits, you can make either a qubit. So on your left hand side, this whole thing, that huge thing, is a qubit.
Mhm.
It's called a 0 pi qubit. And
Okay.
uh, yeah, so this qubit is quite big. It's not very small. It is not as small as a
As
classical
it
bit.
looks.
So
Okay.
yeah, you can see it's 50 micrometer the scale.
Mhm.
So um, the thing is, in order to make quantum computers viable, you need to have these. this qubit size reduced. You need to have as many qubits as possible. And also, when there are so many qubits together, they also talk to each other, and they also talk to each other in a bad way that you don't want. They couple to the environment, and they can decohere, they can lose their information that you stored there, or they can dephase, they can lose their phase, they are no more useful to you. So there are so many challenges that you need to address with qubits, and that's what uh, we are working on right now, or the lab in which I am is working on. And we're trying to make better qubits that are protected from external noise.
Okay.
Yeah, that they don't dephase or decohere. And on right hand side, you see a beautiful pattern. So this is a circuit actually. This is a quantum circuit. Yeah, this is what is possible. This is another application of quantum computing. It's called quantum simulation. Quantum simulation is something. I mean, quantum simulation is what started the field of quantum computing, because you remember Feynman said, "How will you simulate quantum stuff on classical computer?" So this is the quantum stuff. This is the kind of quantum stuff he was talking about. So this is, yeah. So what you see on right is a lattice, and this lattice is inspired from condensed matter systems. And the lab I work in, they showed a couple of years back that they could simulate that lattice with superconducting circuits in one of the fridges I showed you before, and they could see all those properties of this thing. So this is your quantum simulation part, what Feynman talked about, or what Feynman envisioned like in 1980s, and we are doing it now, not at a very big scale, but kind of we are doing it.
Though it's in the beginning stage, we already see so many research stuff going on, and we already see so many trends coming up with all these, which will be useful in the future technologies, maybe for fast computing, fast processing, and everything.
Yeah. Yes, and simulation is very important. So since you asked what is the real life application of quantum technologies, if you can simulate, I mean, to simulate a protein or the dynamics of a molecule is very, very hard for a classical computer because it's classical in nature. But if you're a quantum computer, you can simulate proteins, you can simulate even heavier molecules, and that will help in drug discovery and many other things. So next slide is about it. So this is application of quantum computing. So it will have broadly application with government in the sense like security, cyber security, and defense. In pharmaceutical, in the way that if you can simulate stuff, if you can simulate big molecule, you can make better medicines. Weather services is again, if you can simulate the dynamics of weather, that is still very hard. Still you have supercomputer, but you don't take every parameter in account, and it will be even more accurate. And of course, financial services. So financial services in the sense that stock market, stock market is very random, it's very stochastic, and quantum mechanics is also very stochastic too. So they have something in common. And that thing can be exploited, and quantum computers can be used there. And there are research papers that show that, yes, you have better results with a quantum algorithm. So this is how broadly they are. So in material science, chemistry, measurements, optimization, and cryptography, I mean, it has a lot of applications. I think it will, if it comes to existence, it will affect every area of our life.
Definitely. So we just have to wait and look forward for all these to reach us. Yes. So I have one last question for you.
Yeah.
So most of us here are in our undergraduation and are very keenly interested in research. So how can we start off working on our research career while we are in our undergraduation? Is there any ideal process in specific?
I think it again come back to the same thing. You first, I mean, if you want to do research, that means you are interested in something, right? And you know what that thing is. And then you find like professor or the person who kind of works in that field, and then you approach them. So say someone is in their first year and that person is interested in quantum, and that guy maybe at VIT someone works in quantum computing. I'm not sure, but maybe there's someone who works in quantum computing. I think I would suggest that that person should just write an email to the person who works in quantum computing, asking if he can learn something from that person. So I think that's the first step, to reach out. And if you don't get a reply, say you are at VIT and you want to work at IIT Madras or maybe TIFR, because I know there are people in TIFR working in quantum computing. You keep writing to them. If they don't reply, it's okay. You
For
either
many
send
people.
a reminder, or you write to another person.
Right.
So I think just outreach, just reach out to other people and tell them you're interested and ask them if they can help you. And usually people are very helpful,
Especially in academia.
especially in academia. Yeah, of course. I mean,
Okay.
yeah, kindness is the
Exactly.
kind of pay you get.
Right. So there's endless possibility for doing research in your undergraduate as well. I think this answers your question, Harvinder Singh. Harvinder Singh has another question. He's asking if quantum computers can replace classical computers in our everyday life in future, like you can attend online classes through quantum computers.
See, that far future, even I think I haven't envisioned yet, but I would say even to control quantum computers, you will need classical computers that we still do. So quantum computers won't be a proxy for classical computers. They won't ever replace classical computers because,
Oh.
yeah, they won't. They will be helpful only in some problems that are very specific and that are very crucial to humanity. I mean, as I see it, maybe in next 50 years, when quantum computers are ready, they will be with maybe big research institutes, government services, universities, to research more about other things. I mean,
Right.
if someone can always come up with algorithms where you can make better games or whatever, so that you can use it for entertainment and other things, but to use it for a video call or for day-to-day life, I think no, you still will be using classical
Classical.
computers. Yeah.
I think that answers your question as well, Harvinder Singh. Um, so I think there's another one question from Ashraf. He's asking
Mhm.
if your Cutie Pie initiative is available for beginners as well.
Yes, it is. I mean, yes. So when we ask someone to present on our platform, we always make sure that beginners also understand it. I mean, we try to make sure that beginners also understand it. So it is. Please come and join us. I mean, yeah.
Yes, you can join their Discord community.
Yes, you can. I don't have a link right now, but I can share.
Yeah, you can share it with us. We'll just ensure that
Yeah.
it reaches
Mhm.
them.
Yeah.
Okay, so that was well planned of you to use visual aids because we are able to understand things better, Shashwat. Your intriguing ideas, experience-filled suggestions, and passionate objectives indeed inspire all of us. Like, I think I got answers for all the questions I had. Now let's give
Mhm.
a turn to our audience.
Yeah, sure.
We have a few questions in the chat box, and I would tell if audience are interested, they can obviously unmute their mics and ask their questions. But there are a
Mhm.
few in the chat box, and I'll read it out for you.
Mhm.
So Anubhav Mitta is asking if traditional bits are just charge stored in transistors, right? Similarly, I wanted to know how exactly a qubit is represented in the physical sense.
Mhm. So yes, I think it's an easy answer. You remember I showed you spins,
Yeah.
like an electron had a spin like this,
Mm-hmm.
right? It can be either down or up. So if it is up, it is zero, and if it is down, it is one. And if it is in between, it is a superposition.
Okay,
So
that between state.
this is how a qubit is represented. in physical sense. So it's the spin of an electron.
Right. I think it makes sense to you now, Anubhav. We have another question from Aditya Raj. Traditional bits are just. Okay, so I think the questions are repeated. Okay, we have a question from Sankal. How would we classify quantum computers? Are they digital or analog?
Oh, okay. Are quantum computers digital or analog? I think I don't have a background in computer science, so I'm not sure what it would mean. I mean, but we can think over it. Like, if you give me one example, what it would mean to have an digital 0 1. Okay, so right now
I think you can unmute and discuss if it's required. Just give me a moment. I think I have to unmute. Okay. I think you can unmute now. Okay, I think he's not available. So we have a few other questions.
Good evening.
Yeah, Sankal.
Good evening, sir. So my question is like digital computers are basically they operate on zeros and ones. Like it's basically stepwise. It's discrete versus continuous data. So that's my question, because qubits are, I mean, I find them neither completely discrete because they're in between values, and neither completely continuous.
Okay. Yeah, I think I know. Okay, so the thing is, it will still be digital, because the thing is, when you measure it, it's gonna be in one of the states of 0 or 1. I mean, during a computation, it can stay in 0 plus 1 by root 2, or 0 minus 1 by root 2, or any other weird combination of them. But when you measure them, you're going to have one outcome. And now you measure it, say, infinite number of times. And then you have a probability of having zeros this time, this percentage, and one these many times, or this percentage. And this gives you like how many times you had 0 and how many times you had 1. This comes from quantum mechanics. So I think it still will be digital.
Right. Okay.
Okay, we have a question from Satyajit Mondal. He asks what was the process you went through when you started writing your first paper?
Oh, I'm still writing it. No, wait. So what started thinking? This is what he asked?
No, he's just asking like what was the process you went through, maybe about how you chose your topic, or how do you work on persistently?
I didn't have to do it because my supervisor chose it for me. They told me that's why you need a mentor, that's why you need a supervisor. So they told me, okay, you need to work on this paper. So I was like, yeah, sure, why not? So it's the same. So my first paper that I started writing was about one of the projects I talked about earlier, that was quantum sensing.
Okay.
And so the project was very clear. The idea was very clear in our mind. Everything was set. So there was no problem of where to start. So I think
all you had to do was experiment and write your outcomes.
Exactly. Experiment, or firstly do theoretical research or literature survey. That's also important.
Okay. So I think that answers that.
The answer is just find a person who can advise you. Then it becomes a lot easier to write a paper.
Right. So we have a question from Logesh. When applying for a specialization in physics in a university overseas, what do you look for in a CV, or what are some aspects of CV that will make your CV stand out?
He said physics. So I would say you should have. It depends what branch of physics actually, but I think you should have some research experience on your CV, like a significant one. And you should also have, again, good grades, because you are applying for you're applying in academia, so you should have good grades, and you should also have good referees. That is, your anyone can contact these people, that those are your letter of recommendation or referees, and they can say good things about you. So I think these three things are important. That first is, you can, yes, you have research experience, your grades, and of course your referees. I think these three things are important.
I think that answers your question as well, Lokesh. Um, okay, there's one last question in the chat. Harvinder Singh is asking, in quantum sensing, when the spins interfere with each other, would that not mess up the calculations?
Oh yeah. So that's a good question. I think this is the time I introduce you to some things. Uh, when you have so many spins, they interact with each other in two ways. When they are very close and they go to some, when some condition is satisfied, they go to a state that is called, uh, I don't know. What should it be called? These are decay states. They are called decay states, but they are really good states. They are entangled kind of with each other, and they are better at sensing. But even before going in that state, and during that state also, your spins are talking to each other, and each spin is producing some kind of magnetic field, and
Okay.
that and the other spin is experiencing it, and the other spin is also experiencing other magnetic fields from other spins around it. And this causes some loss in coherence, and that's the biggest culprit in and that's the biggest culprit why you still don't have very high qubit quantum computers, because qubits decohere or spins decohere, and you uh, don't have that those properties that you're interested in anymore. Then you have to start from zero.
Right. So I think you got your answer, Harvinder. And we don't have any more questions for now. So I guess that could be a wrap up. Shashwat, is there anything else you would like to tell the audience?
Yes, of course. I think I should surely thank everyone for attending this event, and thanks to you, Durga, for organizing this, for moderating this, and thanks to Sigma Xi at VIT to invite me here to such a wonderful platform. You guys are doing a really good job with by organizing these events. Not with people only like me. Other people also, when you invite other people, they give you some perspective, and everyone have different experiences. They give you different perspectives, right? And that's what is important. So
Right.
I really commend your efforts towards making research exciting for people in at VIT, and thanks to your whole team.
So the thirst for learning never ends, and I think this evening was fruitful, and we learned a lot about research and quantum technologies. Many thanks to you for joining us this evening, Shashwat, and all the best for your future endeavors.
Thank you.
So I, on behalf of Sigma Xi, thank everyone for joining us. I hope the session was engaging, engrossing, and informative. Do let us know your suggestions by filling out the feedback form in the chat section or by accessing the form using the QR code displayed on the screen. Stay tuned to our social media handles for more updates about upcoming episodes of Rendezvous and many more scientific events. For more opportunities, join Sigma Xi family. We'll be recruiting soon, and our social media handles will start updating you about the recruitment procedure from next week. You can apply for Sigma Xi from VTalk. Contact us for any further information. Once again, I thank all of you for your presence and participation. Stay safe. Thank you.